I would like to describe a field in which little has been done, but in which an enormous amount can be done. This field is not quite the same as the others in that it will tell us little of fundamental physics, but it will tell us much about the strange phenomena that occur just below our perception. In contrast to the natural philosophers of the past, the scientists of this field delve into the recesses of nature and show how she works in her hiding places. Their quest is to understand and create the imperceptible. After all, there is plenty of room at the bottom.
Hello and welcome to the Materialism Podcast, an exploration of the past, present, and future of material science and engineering. My name is Andrew Falkowski, and I'm joined as always by my co-host Taylor Sparks and Jared Duffy. How are you guys doing?
So good. November's here. It actually feels like winter.
Oh yeah, summer was holding on. It had a hot grip on the weather and on the temperature. We had 70s, and now it's finally just plummeted.
You know,
It's
I feel
nice.
like we missed fall a little bit, though. I would have liked some more fall time.
This is always the way it is in Utah. It slams from crazy hot to freezing cold.
Yeah,
every
the
time.
colors don't last a while here.
No.
You got a week,
Yep.
and then it's gone. At the start of the October, I went to a sheep herding festival in Sun Valley.
Oh, I saw that. Yeah, that looked interesting.
Yeah, the colors were really beautiful there. Lots of birch.
I just was so confused because someone was posting videos with no context of like dog chasing sheep around. I didn't understand what it was.
It's a really fun time.
And then he goes, "Yeah, there's a sheep herding festival." I went, "Oh,
I go every year.
I would have gone next year."
Well, it's Thanksgiving, and we have something for you all to be thankful for. We have the coolest of all materials, something that I'm certainly thankful for, which is titanium. Andrew, what are we covering in today's episode?
Yeah, we're going to walk you through a lot of the material motivation for why titanium is such an interesting material and also why it's such a challenging material to work with. But maybe we can start with what makes it so special and why do people care in the first place?
Yeah, big picture. Why titanium?
Well, from a property standpoint, it has a really high specific strength. And then what does that mean?
So specific, you just take your strength and you're dividing it by the density. So pound for pound, this thing really packs a punch.
Or in other words, it has a high strength while being really light. It also has a really nice corrosion resistance because it forms a passive film. That's an oxide layer that forms that prevents further ingress of oxygen at room temperatures. But what's also really strange about it is its history. Despite being the 9th most plentiful element and the 4th most abundant structural metal, it's rarely found in high concentrations, it's never found in a pure state, and mass production didn't start until the 1940s.
Yeah. So that's related to the name, right? This mineral has been like locked away in the earth, titanium. And so the guy who finally figured out how to unlock it from the earth, he named it after the Titans, right? Because the Titans were locked away in the earth, which I think is so cool. Now, we're going to get into that. Maybe we dive in, like who discovered it? What was that process looking like?
Yeah, I mean, so we've known about titanium oxide or titania for a while. It's been used in pigments. It's really white, so white paint often has
if there's white
titanium
paint on the
in it.
wall, it's probably titania.
It's also used in sunscreen, and it's also used in food products. The white icing in Oreos actually contains a little bit of titanium
Shut up,
oxide.
are you for real?
Yeah.
That's wild.
Yeah, supposedly this is food-grade titanium oxide, but we'll see.
Yeah, actually, for those in Europe, you may know it's banned. They banned it 2 years ago, actually. Yeah, America though, you can still get it.
Yeah, we're kind of behind on the food science here.
I just saw a meme, like we just had our election here, and I just saw a meme showing McDonald's fries versus US versus UK, and it's wildly different. We put so much garbage in our food.
Yeah.
Apparently titanium. So, okay, but this was invented a while ago. Technically, they found how to like get metal, titanium, way back in 1791. This guy, I love it. I love these guys back in the old days. He's a /reverend /mineralogist /chemist. Like the guy's just doing it all. And he was in Cornwall, England, for our listeners, in the southwest of England, in the Menniken Valley. You might know where that's at. He found this black sand that's out there. And nowadays, we know that that sand was ilmenite, which is just FeTiO3, so 1 to 1 to 3 there. And basically, after treating it with some acid, he technically was the first person to discover this metallic titanium. Super non-ideal way to make titanium, though.
Yeah, and he names it meconite.
Yeah, because it was the Menniken Valley. It was named after
Yep.
like the location. Pretty cool name, I think, though.
Mm-hmm. It was really just a few years later, 1795, that we get the name that we're more familiar with. This is a Berlin chemist, Martin Heinrich Klaproth. He independently from Gregor isolates titanium from a Hungarian mineral known as rutile.
Yeah, that's TiO2.
Mm-hmm.
So the first guy was FeTiO3. This is now TiO2 as the starting material.
So he starts with the oxide. And just like you had mentioned, because it's entrenched deep in the earth like the Greek Titans, he calls it titanium. But even then, most of the time, this wasn't very pure. And for a really long time, that was really the main method. There wasn't a lot of progress in terms of purifying it. But in the 1880s, there were 2 Swedish scientists who successfully produced 94% pure titanium. This was Lars Fredrik Nilsson and Sven Otto Pettersson. They got it to about 94% pure, and interestingly, Nilsson also discovered scandium.
That's wild. That's
Named
not even
after
that long
Scandinavian-
ago. 140 years ago.
Scandinavian,
That's wild. Okay, so they're making it better. And then it was Matthew Albert Hunter at Rensselaer Polytechnic Institute in the United States. He figures out how to isolate it through something closer to what we do nowadays. He's now starting with titanium tetrachloride as the precursor, and he's adding to that sodium. So there's an exchange reaction in a steel bomb, right? The sodium wants to form sodium chloride, so it's going to strip away the chlorine, leaving behind the metallic sodium or the metallic titanium. So that's a step better.
And apparently it was pretty dangerous too, as these
That's pretty
thermodynamic
reactive.
reactions go. So much so that he actually did most of his experiments at the Rensselaer Polytechnic Institute's football field.
For real.
Like he would just go out there and like run away and set that thing off and let it go because it's open space. There's hopefully no one around. I don't know if the
I want to
University
get
of
away
Utah
with
would
that.
let
But I
us
say
do
Ricycle
an
Stadium, they let me
experiment there.
sneak over there. That's wild to our blacksmithing. So a couple years later, then we finally come to today's process, right? When you go about, if you look up on the Wikipedia page for making titanium, it's the Kroll process, right? Named after Wilhelm Justin Kroll. This is a guy from Luxembourg, and he did a slight variation on what Hunter did. The year's now 1932, and he realizes if you take this titanium chloride and instead of adding sodium, first he tried it with calcium and eventually he tried it with magnesium, and it just works really well. The magnesium does the same thing as the sodium did. It wants the chlorine, so it pulls it away, leaving behind metallic titanium. What I think is wild is that today they still do this in a batch process. We don't have a continuous process for making titanium. How crazy is that?
Yeah, and that's what makes it so expensive too. Despite it having really good properties, because of the lack of a really well optimized process flow, it ends up just being, pound for pound, much more expensive than the alternatives.
Well, Kroll's an interesting character too. He's one of these guys who flees like Europe during the war,
Yep.
and to our benefit, he comes to the United States, joins the institute, like the Bureau of Mines, I think,
Bureau of Mines
and
is
starts
like, you
cranking
need to
out
get on this.
titanium.
Yeah. And so as early as 1944, the Bureau of Mines was making about 15-pound batches, so they could eventually make about 100 pounds of titanium a week. But that wasn't enough.
And what was the interest? Like, what are they? Because okay, it's one thing from a scientific perspective. You got a new metal, but what are you doing with it?
Well, at this time, right, this is about towards the end of World War II. There's desire to improve our aviation capability, and with aviation, it's all about being lightweight and strong.
Yeah, we saw that in the war. Like the Pacific is massive, and we were really limited on the military targets we could hit by how far you had to fly. Now, if you can make a lighter airplane, Jared's going to jump in and tell us all about this. I'm sure he's the aerospace guy, but lighter airplanes mean longer missions, more capabilities, and titanium with its high specific strength, that could be just what we need.
At the same time, the Soviet Union was also very invested in titanium, and we'll get a little bit into their supplies. And so there was impetus for the U.S. to invest in this material. And in 1948, the DuPont company was the first to start producing titanium
DuPont,
commercially.
not just chemicals,
Yep.
metals too. That's awesome.
And those first batches of titanium went to being used on experimental military jets such as the F-84 and the F-86. And in fact, to try to kickstart the industry, the U.S. government, specifically through the military, funded tons of projects, encouraging the manufacturers to substitute steel with titanium wherever possible. Going so far, the Army Ordnance Corporation basically placed an order outset for $1 million worth of titanium metal to try to spur industry.
If you can make it, we'll buy it from you,
Yeah.
basically.
Yeah,
And they did.
One of the earliest uses of titanium that I know of, talking about the planes, is Lockheed Martin. When they were building the F-104 Starfighter, for the exhaust nozzles on the jet, they had to use titanium because it burned so hot that it was like the only material that would really hold up to it. And I think at the time, from the book that we reference in the Radar Absorbent Materials episode, which is called Skunkworks by Ben Rich, he kind of talks about how when they pitched the idea of titanium, it was considered like a really rare metal that wasn't often used. And this would be early 50s around, I think maybe 1951 for the F-106.
The sweet looking plane, dude.
Oh, yeah.
Starfighter. That's rad.
And incredible name.
Oh, yeah.
That's pretty rad.
A little better than a lot of these just sort of acronym things. And yeah, that really signals kind of this change. In about 1951, the Materials Advisory Board projected the need for 30,000 tons of titanium products. But actual shipments were only 75 tons at that time, barely enough for research applications.
And I see a problem coming because if it's coming from rutile minerals, the rutile mountains, that's in Russia. This is during Cold War. They're wanting to do the same things we are. Was this a sort of supply and demand dispute where we're wanting the mineral that they don't want to share with us at this time?
Well, it really came to head when we were building the A12 and the SR-71, which are Mach 3 planes, and so they needed titanium. And so what ended up happening was this was through the CIA and their black budget projects. They actually created a bunch of shell companies, and those shell companies bought titaniums in different amounts.
Oh, what? So they didn't know it was like the U.S. military buying it?
Yeah, and they just brought them all here and then did it here.
Brilliant.
Right, so they sold us the materials to build the plane to spy on them.
Yeah, and then another thing they kind of talk about is once they actually got the titanium, there wasn't a lot of companies that would make these titanium plates. There's actually one company that would mill titanium, and when you'd actually get these like milled plates, the quality was questionable. Sometimes it was really good, and sometimes it was just awful.
Dude, it's a new material. They don't know how to do it yet.
Yeah, from what I was reading, most of the processes we had for steel wouldn't work on titanium. The same parameters for doing things like milling or processing, temperature controls, heating treatments just didn't work.
Even worse, because for planes, the things they're using, a lot of it was also for aluminum. So they had these tools meant for aluminum, an incredibly soft material. And
That's right. Yeah, they were breaking bits all the time. They had to go and not only change their parameters, but also design new steels and milling tools.
They talked about when it came time to really start putting these together, that they actually created like basically a school, like a class where they would teach, this is how you mill titanium. This is what you should do. And I don't remember the number ended up being, but they estimated they saved a lot of money by just teaching people the proper techniques and giving them the proper tools.
And it wasn't just learning how to process it. The U.S. government, the military, was actually a key player in developing what's currently the most popular titanium alloy, Ti-6-4, or titanium 6 aluminum 4 vanadium.
That's like the only one people have ever heard of, Ti-6-4.
It's used in about 50% of the applications.
Okay, yep.
And it really was the military's push to get something that was a good all-arounder, that could be processed easily and had a good balance of properties. And the U.S. gets a lot of focus here because the government basically kickstarted the industry and like carried it to what it is now. But the Soviets also put a lot of effort in. By the 1980s, the USSR, like you mentioned, was roughly 70% of the global output, more than 5 times the production capacity of the US. And they were using it too. They were really interested in using it in constructing submarines. They built about 9 to 10 ships by the end of the 1980s. And the key advantage here was that they had a lower magnetic signature, so it was harder to detect them.
I can't imagine that like the specific strength is the key thing, but it's magnetic signature, so for detection.
It could also dive to greater depths.
Cool.
And so, the U.S. was very worried about this because most of their technology was for combating submarines on a similar level. And so they thought, do we need to make our own titanium submarine? And ultimately, they just designed a torpedo that could go after it.
Okay.
So that ended up being the better solution. So the submarines, they built a lot of those were the Lyra class, and they built one, this so-called Papa class submarine, which could operate far below, any of the contemporary NATO counterparts. But it cost a lot of money to make. Even though they had a lot of titanium, the processing was still expensive. The maintenance was still expensive. Just to build the prototype cost 1% of the Soviet Union's entire 1968 GDP.
Dude, but it looks pretty cool. I'm looking at it right now. That's a cool sub. 1% of your GDP for a single vessel. That's
insane.
Wild. Absolutely wild.
But let's now dive into what makes titanium so special from a materials perspective. Taylor, you want to start us out? Tell us about the phases of titanium.
I was a total novice here, and I underestimated how complex titanium was. It's like when somebody says like steel is just iron and carbon. If you heard our last episode, you know it's more to do it than that, 2 episodes ago. Titanium, in fact, it's a lot like steel. You have a low temperature phase and you have a high temperature phase. The low temperature phase is our good friend, hexagonal close packed. It's actually not exactly hexagonal close packed. It's like a squashed version of it. And the high temperature phase is our friend, body-centered cubic. So right away, anybody who's taken an introductory material science class knows that there's going to be some basic differences in those two structures. By the way, we give these names. The hexagonal close packed we call the alpha phase. The high temperature body-centered cubic is called the beta phase. And there is a transist temperature, right, where you transition from one to the other. It's at about 882 degrees Celsius. The alpha phase, so the hexagonal close packed, where it has fewer slip systems, you could expect it to be more brittle, and in fact it is. The BCC has more slip systems, but it's not just the slip systems. You also have to take into account the slip distance, and those aren't the same. So it's kind of interesting. You have this interesting trade-off. The BCC has more slip systems and a shorter slip distance, which would tell you it's more ductile. But the HCP actually has slightly higher packing on the basal plane. But still, comparing the two, it's no comparison. The BCC high temperature beta phase is much more ductile. The HCP is much more brittle.
Yeah, the other thing you'll know about HCP is they tend to be anisotropic just because of that
one set of
structure.
properties in the basal plane, different ones normal to it.
And that also affects the growth conditions too.
Dude, it's actually 50% difference in mechanical properties. That's very anisotropic. And then just like steel, where steel, you've got your austenite phase and you can cool it down to pearlite band. You get the same sort of things happening with titanium. You got this high temperature BCC phase, and it's cool. If you look at the BCC structure and you cut it right down the middle, if you look at that cross section, it actually looks like the basal plane of an HCP.
Okay.
And that's what happens as you cool it down, that 110 plane becomes the 0001 plane of the HCP.
Is it a diffusionless process?
It can be. There's a martensitic transformation that can take place. Now, it doesn't exactly match up, and so there is actually a slight volume expansion as you cool it down, so that does create some strain. But what's cool is, and what I did not know coming to this episode, this is the reason why it has the unique, they call it the basket weave structure that it creates. If you've ever looked at a microstructure, do yourself a favor, look it up, the titanium basket weave structure. It's super unique looking. It's at very specific angles that you find it at. What's happening is you had the 110 plane, which has 6 planes, 2 directions. So there's 12 ways that slip can happen. And since you're essentially growing these alpha grains out of these big millimeter scale beta grains, they can only grow in like one of 12 directions. So it gives you these cool snowflake or basket weave like microstructures. That's 100% due to the transformation that takes place between this high temperature and low temperature phase. Pretty cool.
Yeah, some of the sources we read call them colonies or packets of lamella.
Yeah.
And depending on how quickly you cool, as you would imagine, you also get different growth conditions. If you cool quickly, you'll get very fine. You cool slowly, you'll get much more
just like
coarse.
with steel.
And if you quench it, as we mentioned, you'll get this martensitic transformation as well.
Yeah, there's 3 tools that you have in controlling your microstructure. There's like deformation, which we haven't talked about yet. Okay, let's say you cold work it like crazy and you really mess up that lattice, so now it's heavily distorted. Well, eventually recrystallization is going to take place. You're going to grow new grains. And now you're not confined by that basket weave structure, so they can become equiaxed. You get nice round grains if you cold work it like crazy. So that's one thing you can do. And obviously the temperature you do that at, the degree, the mode, the rate, all those things. The second thing you have to control the microstructure is the annealing temperature, right? Which is, this can be done above the transit temperature. You can take this back above to the beta region, right? And then finally, there's the aging temperature, which is, think of it as a low temperature annealing. Some combination of those 3 things gives you the ability to have crazy variety of structures. It could be basket weave, it could be equiaxed, it can be a mixture, they can be really fine, they can be really coarse. You have a lot of tools, and therefore the types of structures that you can produce are very varied.
And the properties.
Yeah, and the properties are tied to those. Yeah, so just one last thing before we leave microstructures. I just think it's wild. Like in material science, it's all about understanding structure, property, processing relationships. And really simple ones exist, like Hall pitch, small grain size, hard material. But this is way more complex than that. Because, for example, you've got 2 different types of structures, lamellar, equiaxed, and they can exist at fine or coarse. So you have like 4 degrees of freedom here, right? And if you look at how those 4 degrees of freedom impact the different properties, it's crazy complicated. What might be beneficial for one property like modulus could really hurt something like ductility, creep, fatigue crack growth, plasticity, oxidation behaviors. All of these have to be understood in the context of microstructure. And there's not like one structure that's always better. It's not like you always want fine-grained basket weave, for example. It really is complex, which is why I now realize why people in my field spend their entire career just being titanium experts.
Yeah, and if you think about it, it makes sense too, right? Like the lamella structure is really good for fracture toughness. And it's just the same mechanism as like beta silicon nitride, where you're just creating a really contorted path for crack growth.
There's a good chapter on this. I'm just going to read one brief paragraph because they summarize at least some key takeaways. Here's what they have to say about it. They say, okay, fine scale microstructures, they are going to increase your strength as well as ductility, but they also retard crack nucleation and they are a prerequisite for having superplastic deformation. So if you want to deform it, you got to have a fine structure. Meanwhile, coarse microstructures, they are more resistant to creep and fatigue crack growth. So for some applications, turbine engines, like this is going to be dominant. And then it says equiaxed structures also tend to have high ductility and fatigue strength, but they're definitely preferred for superplastic deformation. So it's not like you always want one or the other. It really depends on the application.
Yeah, and there's also a big chemical component to that. There's like 100 different commercial titanium alloys that are all based on these additives. And the additives also affect the structure that forms and the structure that's stabilized. So maybe we can get a little bit into that. When you're talking about different elements that you can add to titanium, there's about 3 effects. There's some that are neutral. 6-4,
that's 6% aluminum, 4% vanadium. Presumably these are doing something very specific, right?
Yeah, so some elements are considered neutral. They don't affect the phase diagram. Some are considered alpha stabilizers. These are going to increase the temperature range at which the alpha is stable. They also
The lower temperature phase.
Yeah.
Okay.
They also create an alpha plus beta region.
Mm-hmm.
So now you can have a mixture there. And then you have two types of beta stabilizers. You have some that will bring down the beta phase, that high temperature BCC, make that stable at lower temperatures. Then you'll also have one that forms a eutectoid.
So if you bring, I get this, because titanium, its high temperature phase is BCC.
Mm-hmm.
But what if you add something that stabilizes the BCC, but it's not the same crystal structure? So you have to have a eutectic at some point.
Yeah.
So if you add something that's FCC or whatever else, what things are there? Like molybdenum, right?
Yeah, so for the eutectoid, it's iron, manganese, chromium, cobalt, nickel, copper.
Yeah, different structure. They're not BCC.
Yep. For the isomorphous, also BCC, you have molybdenum, vanadium, tantalum, and niobium. Alpha stabilizing elements will be things like aluminum, oxygen, nitrogen, carbon. And then your neutral ones are tin and zirconium.
So why add something if it's just neutral? If it's not modifying the transist temperature between alpha and beta, why add those?
They primarily just strengthen the alpha phase.
Okay, solution strengthening.
Mm-hmm.
Okay, so we have a lot of variety then, because it's not just now just alpha or beta. You can now stabilize mixtures, one versus the other. So this gives rise to classes of titanium. You have your alpha class, near alpha, your alpha plus beta, and then your beta.
And your metastable beta.
And metastable beta, right.
So before we dive into maybe where these specific classes are being used, let's broadly talk about which phases generally have which properties and why you'd want to be maybe near alpha or why you'd want to be metastable beta.
Okay, yeah.
So the alpha titanium alloys boast really good corrosion resistance. They're also very weldable, so they find themselves in a lot of high corrosive environments. They also have a really low diffusion rate, so that's why they're not going to be susceptible to attack as easily.
You also don't have to add as much weight fraction of the secondary phase.
Yeah.
And that secondary, these other chemical additives are the ones that are most prone to corrosion, for example.
And you'll also get resistance to plastic deformation, fracture toughness. You get great creep resistance, and they're generally low density because aluminum is your primary alpha modifier.
Gotcha. You're not adding something heavy like molybdenum. You're adding something with a really low density.
So for high creep applications or high fatigue, it's typically going to be alpha titanium.
Okay. So what about beta then? It's the opposite of these properties?
Yes and no. It tends to be very confusing. With so many different additives, it's hard to have any sort of hard and fast rules because some will increase your modulus, some will increase your machinability, others will do the opposite. But generally, the betas are known for having high strength. They also are very versatile in their properties, but they tend to have lower modulus, lower ductility, a very small processing window. They're much harder to process, but they have really great hardenability too. Adding all these things, you can imagine you can precipitate secondary phases.
They're worse for corrosion and they're worse for welding. It's very hard to weld these.
Yep.
Welding titanium period is hard, but these are especially bad because all these additional components you're adding, they segregate into that heat-affected zone and then they form brittle intermetallics, which is not what you want when you have a weld.
No, and this actually caused a lot of issues on the SR-71 project as well.
Yeah, so this was an issue that they actually didn't know what it was in the beginning. Basically, they kept having bolt heads strip off, and they weren't sure why. And the culprit ended up being they used cadmium-plated tools on their titanium bolt heads.
Cadmium hardens the tool.
Yeah,
okay,
and so
right.
when the little bits of cadmium get left on the titanium,
like tiny surface levels.
Yeah, literally, just that was all it took.
Cow.
As the temperature increased during these tests, it would kind of mix together, and then basically at some point you'd switch from ductile to brittle, and then your entire bolt head shear clean off.
Intermetallics, man.
And that would be such a hard problem to find too.
Yeah,
you would never suspect that trace amounts would cause that
That's
much
wild.
of an issue.
It's impressive they figured it out. I guess maybe because they saw it was only focused on the bolt head specifically.
But dude, you told me about another story. It was like the marker that they used was actually also causing corrosion?
Yeah, so when they were drawing lines on the sheets of titanium, just like marking things, they used, they even called a brand out. They used Pentel pens. And I guess in that pen, there's a chlorine-based ink. And when they would draw on it, it would actually etch into the titanium itself.
No way. And probably damage that titanium oxide layer. That's your corrosion protection.
Yeah, when I was trying to figure out the origin of this, because titanium is used as the go-to material in
corrosion resistance is one of the reasons.
Right? It seems to be related just to the alloy that they were using. It was likely a beta titanium, and didn't have nearly as much protection. That or the friction wiped away or like removed that that protective layer. What's really interesting is apparently aerospace companies these days, probably because of this story, are like hyper intensive about which markers are allowed to be used to mark samples because
dude,
this is
awesome.
apparently a constant issue in specialty alloys.
It's so weird.
And then wasn't it also something about the water?
Yeah, so the other thing, and this kind of ties into the weldability of it, when they would weld these two pieces together of titanium, in the summer, the welds would fail more than in the winter. Things that were welded in the summer and welded in the winter. And it turned out that Skunkworks is in Burbank, and so I guess they had to add a lot more chlorine to the water supply in the summer to prevent algae growth.
For real.
And so when they'd wash down the welds afterwards,
I wonder who's the clever engineer that finally like solved these unsolved mysteries, like traced it back to that. That's wild.
But when it was all said and done, I think like with all of the problems they solved and everything they fixed, I think they estimated they saved like $20 million in mitigating all these issues ahead of time and also getting the right tools.
Worth it to get to the bottom of it.
Yeah.
Mhm.
Hire yourself a material scientist, get to the bottom of this stuff. All right, Andrew, we've got 4 classes of titanium alloys. What are we using these things for? You've already said that like there's hundreds of alloys that have been made, and yet we really just use Ti-6-4 predominantly. But there must be other applications.
So we can start with the alpha alloys. As we mentioned, these are primarily used in your chemical process engineering, mostly because of their excellent
Better corrosion
behavior,
resistance.
deformability.
Yeah.
Yep. You'll also get a lot of what they'll call commercially pure titanium grades, and these primarily just differ in the oxygen content. So titanium can absorb like 15 weight% oxygen and still maintain its phase. And that's
Wow.
bad. But adding a little bit, it goes to those interstitial sites and it strengthens it.
Okay.
So most of these grades, like grades 1 through 4, are just slowly increasing the amount of oxygen that's added. For really high corrosion protection requirements, there's a palladium-containing alloy.
For real?
Grade 7.
That's not going to be cheap.
No, it's insanely expensive. So there's another grade that is often preferred that's a little bit cheaper and offers comparable performance. If strength levels for an alpha alloy are really, if high strength is required for an alpha alloy, you'll get this Ti-5 2.5 or titanium 5 aluminum 2.5 tin, which is typically a good choice. The near alpha titanium alloys are your classic high temperature alloys. This class is ideal for anything that needs to go to a really high temperature and also have good creep behavior.
Yeah, and you mentioned high temperature, but it's not as high as you might think. For these alloys, you're really limited to about 500 C, maybe 550. If you want to go higher than that, you got to move to a different system altogether. We'll talk about that in a minute.
That's right. Yeah. Temperature is always this weird thing. Like high temperature for metals is very different than high temperature for ceramics.
Yeah.
Whenever people say that, it's like, well, who's high temperature?
Yeah.
But what you'll also see a lot with these near alphas is additions of small amounts of silicon, because they segregate to the grain boundaries and they
Creep.
inhibit.
That's going to be for creep for sure.
dislocation climb.
Yep.
And so there's a lot of variations where here's a common near alpha alloy plus a little bit of silicon.
Okay.
The alpha beta alloys, these are most common. This is what Ti-6-4 is.
When you say alpha beta, we're talking about significant fractions of both.
Yeah, about how much are we adding?
So for beta stabilizers, you're adding about weight percent, up to 6% weight percent of the beta stabilizer. And the volume fraction of the beta phase itself can be anywhere from 5 to 40%. So these can be significantly, equal amounts of the phases, basically.
Mm-hmm. And these, just because of their nice all-around properties and their them being very mature, this is what you see the most in the aerospace industry as well.
So this is Ti-6-4.
Yeah.
Okay. And then you've got 2 other ones, metastable beta and beta. Where do we use these for?
The metastable beta alloys occupied this kind of weird space, very much designer alloys, but these can be hardened to extremely high strength levels, more than 1400 megapascals.
Oh, now you're talking. Awesome.
Mm-hmm. And the complex microstructure really gives a lot of freedom to try to optimize and balance strength and toughness. So these are going to be primarily used in really specialty applications where you need that performance. And finally, the beta titanium alloys, the most versatile, but they're kind of problem children to work with. The main ones that you'll see are these titanium 1023, beta C, Ti-metal 21S, a lot of commercial names that don't really tell you what's going on inside them. But these see a lot of use in structural components. Ti-17 will be used for gas turbine engine compressor discs a lot, applications where there's high cycle fatigue strength necessary.
So if you look at the sort of diagram of near alpha, near alpha, alpha beta, to get all the way to the beta stabilized, you are adding a lot of these modifiers.
Yeah, like 30 weight percent.
Yeah.
Which is a lot. And
like,
that's
are you
why
still
the
titanium
process-
alloy? Yes, but you're really moving out.
Yeah, and with that many, all of a sudden you've exposed yourself to tons more processing issues.
For sure.
Right. New reactions can happen. New intermetallics can form. It's going to be harder to get a handle exactly on the chemistry. It's not going to be as tight. And that's why we saw so many issues with these early programs with titanium. But there's another class of titanium alloys that has gained a lot of interest, and where a lot of the titanium alloy development has gone. I think a whole episode should be dedicated to this, but it's worth mentioning the titanium aluminides. We mentioned that the temperature performance isn't as great, only about 550 C. And that isn't anywhere near where it would need to be to try to compete with nickel superalloys. And that primarily happens because of poor oxidation resistance at high temperatures. You would think that the passivating film holds up, but once you get higher, it becomes disordered and it grows. The kinetics take over. And even when you alloy a little bit of aluminum in there, you don't get the nice alumina formation, because even though alumina is more thermodynamically stable, the titania formation is kinetically faster, and so it wins.
So what's happening is like we've been adding aluminum to stabilize the alpha phase, but when you say titanium aluminides, you're going way beyond just the solubility limit. You're moving to the region where now these are intermetallics. You're forming an intermetallic.
Yeah.
And it's of the 4 intermetallics that they can form, 2 of them are brittle and 2 are ductile. And these are 2 that are relatively ductile as intermetallics go, basically. And the benefit is that now you've pushed your operating temperature up basically 500 more degrees. You're around 1200. You can operate these things.
Yeah. Which allows them then to enter the space of some of the superalloys.
Competing with nickel alloys and others.
Yep. And so some of them, I guess, more advanced ones are the ones that are kind of currently the kings of this space. Add a little bit of niobium in there too.
So let's back up a minute. Like, that's one option for getting to high temperatures, but why can't, like, titanium doesn't melt at 500. Why is corrosion such a problem above 500? I thought that we had this awesome TiO2 layer that was protecting it. Why are these still getting bad oxidation behavior?
Yeah, so it ends up being a lot like aluminum at higher temperatures, where although at room temperature you get a nice passivating layer, once you start going up in temperature, the kinetics increase pretty significantly on your growth, and the TiO2 phase starts to become disordered such that it doesn't inhibit. And what's kind of interesting is, even though adding aluminum extends your temperature window a little bit, it's not a catch-all. Even though alumina, the oxide, is more thermodynamically favorable, just barely, than titanium oxide, the kinetics of the titanium oxide are so much faster that it ends up breaking that up, and you get a discontinuous layer, and there's nothing to prevent ion transport.
Yeah, if it's not a dense passivating, well, if it's not a dense layer, it's not passivating.
Yeah.
So if you're growing the Swiss cheese layer on top of it, it's still got a pathway for that oxygen to get in and corrode.
Mm-hmm.
Oh, interesting.
And so it seems a lot of the research.
So could you just slow down the growth of that? Are there additives to slow down the growth of that layer and therefore make a better layer?
That's where a lot of research is in. Going all the way back to our episode on thermal barrier coatings, that's also a big potential option here, is to basically just put a known cohesive layer that will prevent oxygen diffusion.
So properties aside, I know obviously that it's used a lot in airplanes, but where else do we end up using it?
I'll leave it to the mechanical engineer. He wants to know about applications. All right. Well, we use it all over the place. Anytime you've got something that has this excellent corrosion resistance, we're definitely using chemical processing. So places where you don't want things to corrode, titanium might be the right option. Japan, for example, 30% of their titanium that they're used goes right to chemical plants. Not surprising. Oxidizing chlorides, for example, good application.
Yeah, you also find it in heat exchangers, mainly because, one, it can operate in really corrosive water environments, but it also has a higher thermal conductivity than stainless steel, which makes it better.
Fantastic. Yeah, that's the heat exchanger's job.
Marine and offshore structures along the same line are also find a lot of use in it, where you don't want corrosion by seawater, or for critical components that are going to be operating in just really gross, nasty, like saltwater, hydrocarbon environments. That's really the go-to there.
And anything that's good for aviation because of its specific strength, obviously, especially if it gets cheaper, would also be good for automotive. So I'm not surprised to see the automotive. Most recently, we've seen it in the latest iPhone, right? The iPhone 15 is bragging about titanium. I think this is as much of a gimmick to get people excited about it as hype as it is for actual applications. But yeah, it will reduce the density. It will reduce the weight.
A lot, especially on some of the more expensive cars. Like I know Bugatti has a few titanium parts, and I think some of the Corvette may have a few titanium parts. I think definitely as the money goes up, they're more willing to use titanium parts.
For sure.
But it opens up a lot of other opportunities, because it's not just weight savings. As soon as you cut your weight in one area, you can now open up new opportunities for redesigning parts. All of a sudden, the loads that other parts are experiencing aren't as strong, so they don't need to be.
Yeah, or the dimensions of the part, right? Can do the same job, but in a smaller dimension. Maybe that opens up area where you could do something you couldn't before.
Sporting equipment's another good area, right? That's always about having lightweight, strong materials.
Yeah, I've seen some climbing gear that's made of titanium. I don't know if it's worth it, but you can buy it.
Probably bike frames as well, although I feel like they're going composite for
Yeah, for
most of it.
sure. So the coolest thing I think was in the medical field, though. That's where we really use these like crazy. How come?
Yeah, I mean, you see them everywhere. Most implants are titanium, or at least have some titanium on
Yeah,
them.
hips, knees, all over.
And it really comes from this experiment done by, apologies to the
To the Swedes.
Swedish, yeah, Per Ingvar Brennemark. He used a titanium optical chamber this is in about the 1950s, I think.
Optical chamber?
Basically, he was trying to study healing in rabbit bones to try to understand this a little better. And so he basically used this to create an adapter,
window?
a window effectively that
Oh
he
my
could see in
gosh.
with a camera, which is really gross. But after the experiment, he observed the healing. They're like, okay, we can remove this optical chamber, and they couldn't get it out. The bone had grown on it and attached itself. And this was the first time that someone had seen this. And he describes it as osseointegration.
Osseointegration. Okay, so bone integration.
And as soon as he saw this, he realized the impact of this, and he completely pivoted his research to this, going so far to research on his own students, where he implanted small pieces of titanium in their arms and showed that the titanium could be safely implanted in the body with no effects. That was
For
probably
extra
the deal.
credit. For extra credit.
He's like, if you want to graduate, you're going to have to put this in your arm.
Holy cow. When was this? 1950s? It's not even that long ago. That's crazy.
And it also extended then into the dental implant area.
Yeah,
as
they
well,
call him, he's
because-
like the father of modern implant dentistry. That's pretty wild.
Yeah, I think early on, they were looking for someone to do a trial on, and someone said, I want my teeth fixed, and he was willing to go through with it, and he got these titanium dental implants, and he was able to use them for 40 years.
So just doing a bit of Googling on why it's such a good material for osseointegration, it sort of lists these 5 things. One is like biocompatibility. First off, your body doesn't hate that it's there. It's not trying to get rid of it. It's like, all right, cool, titanium, right? Second is it has this oxide layer, which is good for anti-corrosion. That means that your bodily fluids are not going to be attacking the metal itself because it's protected. The mechanical properties is the one I mentioned, that it sort of matches bone. You can actually do surface modification. You can make it change things like the roughness or active layers on the surface, or you can put chemicals on the surface that will sort of stay put. And then last thing is just corrosion and fatigue resistance. We already talked about this is a good fatigue material. So kind of the perfect material for bone. That's pretty awesome as implants go. This has been a super fun episode. We have learned a lot. I personally I was naive about titanium. I definitely appreciate the complexity of this amazing material much more. It's fun to learn about and fun to record with these guys. One of the things that was my takeaway from this episode is titanium is hard to work with. It has some narrow processing windows. The ability to actually manufacture this is one of the limiting steps on our ability to use it, which ties in wonderfully with one of our amazing sponsors, Cal Nano. In fact, they were talking to them about titanium, and they brought up like, oh yeah, actually they have a unique tool. It's called an Aerospace machine. This is something that can selectively load different powders into complex shapes and then do SPS on them, which if you're trying to make a very specific mixture of beta or alpha modifiers or whatever it is to make a specific grade of titanium, and you got to shape it into a shape, like this is what you're looking for. So we are proud to be associated with Cal Nano. They've been amazing partners of the show for a long time. So give them a look. We think that they're pretty awesome.
Materialism Podcast is also sponsored by Materials Today. You can visit materialstoday.com to stay up to date on the latest happenings in the material science field and read some of the fantastic articles that they've published. You can also head over to elsevier.com to find out more about their journals, books, conferences, and related programs.
And then one last thing. It's Thanksgiving. If you're thankful for this show, will you leave us a comment? We're thankful for you guys. In fact, we would love to hear your feedback. So you can drop a comment on the YouTube videos, on our Instagram, shoot us an email, materialism.podcast@gmail.com. Whatever would float your boat, we would love to hear back from you. Give us a review. We think that'd be great. And obviously, we are grateful for the people who made the show possible, for my co-hosts. And obviously, we are super grateful for the people that make this show possible. Our music comes from Kolobyte. You can check him out on wherever you listen to music. Okay, and with that, we will see you guys next time.
The inventors of fire, electricity, magnetism, iron, lead, glass, silk, cotton, the makers of tools, the captors of lightning, the architect, the engineer, the musician, are all beneficiaries of the materials of this world and are bound only by their imaginations in manipulating those materials.